Hi everyone, my name is Roshan and I'm going to present our paper on anticipatory planning. We consider a household robot given a sequence of high-level tasks, each one at a time. Imagine a robot is tasked with clearing the dining table. Most existing task planners have immediate solution of moving the plate away to the closest location, which in this example is the desk, as illustrated inside the yellow box. This plan produces side effects for subsequent tasks, such as clearing the desk and or cleaning up the plate, which happens in the sink. This plan will also make these subsequent tasks more costly. However, if the robot was given all the tasks at once, existing planners could be used to find the minimum cost plan for all the tasks using the shown equation without any problems of side effects. This could be seen in the example in the blue box. However, the robot does not have access to the future task when trying to solve a current one. Therefore, we assume there exists distribution over the tasks which are inherent to the environment. In this example environment, the distribution could be comprised of 4 tasks sharing the same probability. Here is 0.25. This will allow the robot to seek a policy that minimizes the expected cost of the future task, which is the aim of anticipatory planning. We only consider pick, move, and place type of task, and they are specified using PDDL. We use A-star search to solve the planning problems to get the cost of the immediate plan. Pick and place have constant cost, whereas move has cost coming from motion planner using lazy PRM algorithm. We introduce anticipatory planning so as to minimize the joint objective of planning cost for the current task and the expected cost associated with the future task. Given access to the task distribution, the robot could compute anticipatory cost and consequently find a best intermediate state for next task. Reasoning about future cost over a long sequence of tasks is computationally challenging. And so we instead seek to minimize the expected cost associated with an immediately available task and a single next task in the sequence. Anticipatory planning involves first moving from a starting state to some intermediate goal state from the set of goal states in which the given task is completed, and then subsequently completing another task in the distribution. Even when the robot is not assigned an immediate task, anticipatory planning can inform how the robot can reconfigure its environment so as to reduce expected future cost when it is eventually given a task. We call this objective as preparation. During deployment, computing anticipatory cost is often challenging because there can be hundreds of possible future tasks or the robot does not have direct access to the task distribution. Therefore, we train graph neural network to estimate anticipatory cost. We turn environment state into graph and feed the graph into GNN to estimate the cost. We use 3 sets-count layers followed by liquid. The output is then fed into min pooling layer and finally to the linear classifier to get the output of the graph. To train GNN, we generate data from 250 training environments and 150 distinct testing environments. We randomly sample 200 states in each environment and compute the cost for each state. Each label datum consists of the graph of the state and its anticipatory cost. To obtain this data, we solve each planning problem instance from task distribution. We use RM optimizer on PyTorch and train for 10 epochs using learning rate of 0.01. It is challenging to enumerate all the states in complex environment. Instead, we rely on an iterative procedure as shown here to search more efficiently over states, likely to improve the total cost. There can be many alternate goal states, from which we find an intermediate goal state that is more suited to paying down the overall cost. Similarly, for preparation, we follow hill climbing optimization approach for the search. For 200 iterations, the robot randomly samples tasks from the task distribution and evaluates whether the anticipatory cost improves along the way. We evaluate performance on a 2D blockworld environment using 4 planning approaches, of which myopic is a baseline, whereas other 3 are our learning augmented approaches as shown here. We handcode the task distribution with 20 to 25 tasks based on the environment. We highlight one result scenario in which we see the total planning cost of the sequence is decreasing. Under our anticipatory planning approach, the white block F is moved directly to the white region, avoiding this side effect at the expense of a small initial cost. When allowed to prepare the environment in advance, both planners, myopic and anticipatory planning improves performance as you can see here. Here are our results in the table, which shows anticipatory planning reduces overall planning cost across all sequences by 5% and even more with preparation by 11%. In this plot, we show the average planning cost of each task with all four approaches and see our approach improves cost across the sequence. This result was from 32 unique environments in which we evaluate over 100 10-length task sequences drawn according to the distribution. Summing up, anticipatory planning guides the robot towards behavior that improves overall planning cost of a sequence given only one task at a time. Furthermore, with preparation, the robot prepares an environment in anticipation of future tasks. In future work, we seek to apply this approach to guide integrated task and motion planning. Thank you.